reactant for cellular respiration. All right, so what is the products of photosynthesis? So products of photosynthesis are coming out of photosynthesis. What's one of the products, Joe? It's a product of photosynthesis.
ATP?
Nope,
I'm sorry.
photosynthesis. It's what goes in to cellular respiration.
Glucose.
So let me change this.
Glucose.
What's a reactant to cellular respiration? Yeah, glucose is one of those products of photosynthesis that's a reactant for cellular respiration. There's one more. Oxygen. And so plants give off the oxygen that are used by all organisms that do cellular respiration. So then the products of cellular respiration are the reactants for photosynthesis. So what's it, therefore, a reactant for photosynthesis, Devin?
Carbon dioxide.
Yeah, carbon dioxide. So 6 CO2s. And then what's the other reactant for photosynthesis or product of cellular respiration? What do you think, Nathan?
The other product for, oxygen. H2O.
H2O. All right, very good. And so therefore these guys are related in that they are opposite reactions. So for cellular respiration, we've been writing, the reaction like this. All right, well, 6 O2 gives you 6 CO2s and 6 waters. So that's cellular respiration. And therefore photosynthesis is the exact opposite. These things go in, these guys come out. All right, and so photosynthesis is taking the carbon dioxide and taking the water and converting it into glucose. And then that's the main thing. And then it gets rid of oxygen, that's the waste product, which is good for the rest of us. And then this is, as Roman said, this is an endergonic reaction. And so where does the energy come from in this endergonic reaction? Endergonic reactions means that they need energy. The energy actually comes from the light energy. So that's where the sunlight comes in. And so photosynthesis is really a big energy conversion. We take light energy and convert it to the chemical energy in glucose. And then we take that glucose and break it down in cellular respiration, which releases energy to make what? All right, to make ATP, and some of it's released as heat and increases the entropy of the universe. All right, so that's our overview here. And so some terminology here we're going to look at with this. So this overview of photosynthesis. So photosynthesis is the process that converts light energy into chemical energy. I'm going to leave this up because I want to write on it. Unfortunately, it is right. When they put it in my projector, they didn't center it on the whiteboard. And they tell me that they can't fix it. So for the rest of my life, this problem. So that's what we call teaching problems. So it's really frustrating though. It's like you can't really just change the angle just a little bit, They tell me no. And then I wanted them, and then I really didn't like it when I asked them to move it over here in the center.
Solar.
All right, so that was real, but they can't even change the angle. All right, so we have to.
It says solar.
All right, so we have this light energy converted to chemical energy, as I said, it's a big conversion. So directly or indirectly, photosynthesis nourishes almost the entire living world because everything either eats a plant or eats something that ate a plant. So when we talk about plants doing photosynthesis and cellular respiration, do you guys remember which one happens more? Photosynthesis, because if every time a plant made a glucose molecule, it broke it down to get energy, there would be no glucose in our plants, and when we eat the plants, we'd never get any energy. So some of that glucose actually doesn't go directly to be broken down. Some of that glucose is stored in the plant, and that's why organisms can eat plants and get energy from them, or you eat something that ate a plant, all right, and so on. That's what it means by directly or indirectly. So autotrophs sustain themselves there a little bit without eating anything derived from other organisms. So you guys know that you guys have heard of this word autotrophs before. So auto means self, troph is feeding, so they're self-feeding. They don't have to eat anything, and so they can make their own food with energy from the sun. We can also call autotrophs, they're the producers of the biosphere, producing organic molecules from CO2 and other inorganic molecules. So, or producing things like glucose, but from carbon dioxide and water. And so the word producers, they mean that they produce their own food. So in this case, organisms that do photosynthesis produce their own food. So autotrophs and producers are referring to the same types of organisms. Almost all plants are photoautotrophs, using the energy of sunlight to make organic molecules from water and carbon dioxide. Photo means light, and autotrophs means that they are self-feeding, so they are self-feeding using energy from light. So that's what so they do photosynthesis, is basically what a photoautotroph is. Not all organisms, not all producers actually do photosynthesis. Let me give you an exception. On the bottom of the ocean near hydrothermal vents, they're so deep in the ocean that the light doesn't get down there. It's filtered out, so it's pitch dark, but you have this whole ecosystem of organisms that live there. And so how do organisms live there if you don't have any organisms that are producers? Well, you do. There are certain organisms that instead of using light for energy can use other sources for energy. And so near these hydrothermal vents, there are gases that come out, and hydrogen sulfide is one of the molecules that come out. And there are actually microorganisms that can use hydrogen sulfide as an energy source to make organic molecules. So these bacteria and these microorganisms can use hydrogen sulfide, they make their own food, they're able to survive. And then guess what? If you have organisms that are able to survive off of these gases, then you can sustain other organisms, because then they can eat the microorganisms and you can have food chains down there. And so you have this whole little ecosystem. So the producers at the bottom of the ocean aren't photoautotrophs because they're not using light energy, they're using energy from this chemical hydrogen sulfide. We actually call those chemoautotrophs. They can use chemicals to sustain and make their own food. So I just wanted to explain that there are exceptions to that. Right, so what kinds of organisms do photosynthesis? So we all know plants do. Algae in the ocean and lakes, ponds, and so on. Certain other protists. Protists are unicellular, and they're only one cell big, eukaryotic organisms. Eukaryotes. What does that mean, eukaryotes? What's true about their cell?
They have organelles.
They have organelles. They have a nucleus and all the other organelles. Some prokaryotes can do photosynthesis. What's a prokaryote? What's an example? Bacteria. So that's bacteria. So some bacteria can do photosynthesis. Where does photosynthesis take place in the cell? A chloroplast, right? Does bacteria have chloroplasts? No, all right. So we're going to look at a little bit later how in the world do some of these bacteria do photosynthesis without having a chloroplast, and they can. All right. So we'll come back to that. So the organisms that do photosynthesis not only feed themselves, but also the entire living world, and they can do that because they store some of that glucose that they make. And so this is just some pictures of the forest, the plants, algae in fresh and salt water. Here's a euglena, which is a protist that does photosynthesis, and some bacteria do photosynthesis as well. All right, so most of the organisms on Earth are not autotrophs, they're heterotrophs. They obtain their organic material from other organisms. We are heterotrophs, so we get things get our energy by eating other organisms, either a plant or something that ate the plant. So therefore, heterotrophs are also called consumers. Almost all heterotrophs, including us as humans, depend on the photoautotrophs for food and oxygen. So we depend upon the algae and the plants to make glucose and store some of it so we can eat them, and then release oxygen into the air so we can breathe it in. All right, so now we're going to look at and talk about the photosynthetic process more specifically. And so the chloroplast is where this occurs. The organelles that are responsible for feeding the vast majority of organisms. Chloroplasts are present in a variety of photosynthetic organisms, like the protists and the plants and so on. So, did I go too fast? Good.
No, you're good.
So where does photosynthesis occur in most plants? The leaves. So while the stems may be green, like of a daisy or something like that, they can do photosynthesis, but the majority of the photosynthesis occurs in the leaves of the plant as the greatest surface area to absorb light and so on. So their green color is from chlorophyll, the green pigment within chloroplasts. Let me draw up here on the board. So we have the chloroplast here. You remember from the cell chapter that chloroplasts have stacks of discs. They're called thylakoids. Do you remember this? And it's the whole stack is called a granum. So chlorophyll, I'm sure you've heard of chlorophyll and know it's green. It's a green pigment. Where these pigments are in the membranes of these thylakoids. And so you have these pigments. What a pigment does is absorb light. And so in this case here, we said that photosynthesis is an endergonic reaction. It needs energy from the light. So when the light shines down on the leaf, it goes into the leaves, it goes into the cell, and is absorbed by the pigments in the chloroplast of the cell. And so that's what chlorophyll does. It's the main photosynthetic pigment to absorb the light. So what we're looking at here is so the light energy gets into the plant and gets to the chloroplast with the help of these pigments. So light energy absorbed by chlorophyll drives the synthesis of organic molecules, that's glucose, in the chloroplast. So we're going to use that light energy to help make the glucose. And then, remember at the bottom of the leaves, I've talked about this before, are small pores that open and close. These small pores are called stomata, and that's where gas exchange occurs. So CO2 comes in, and so how does the CO2 get to the leaf? It goes in through the stomata, and is used to make glucose, and then O2 leaps through that pore. Chloroplasts are found mainly in the cells of what we call the mesophyll layer of the leaf. Meso means middle, so it's the cells in the middle of the leaf. A typical mesophyll cell has 30 to 40 chloroplasts, so there's a bunch of them. And the chlorophyll, where that's at, is in the membranes of those thylakoids. And the thylakoids are in stacks called granules. So that's what we just went over. And then also in the chloroplasts, another important part for photosynthesis is the fluid that the stacks, the granum are floating around in. That fluid is called the stroma. That's going to be, so the thylakoids and the stroma are two places inside the thylakoids that are going to become important to us. So you have this picture here that shows you kind of the breakdown of how things that are needed for photosynthesis get there. And so that picture right there is right on that crack there. So I'm going to use the overhead to draw on it because I wanted to draw on this picture here. So you have the leaf, And what this is showing is if you were to look at the thickness of a leaf, like a leaf, you don't think, you know, it's pretty thin. You wouldn't think that there's a lot going on in there, but there is. And so this is like if you were looking at the thickness of the leaf. So I'm going to write a few things on here that aren't on here. So on the top of the leaf, so this is the top and this is the bottom. So you can see that the holes, the stomata, are at the bottom. The top of the leaf, I drew a green line here. Most leaves have what we call a cuticle. The cuticle is a waxy layer. Can water get through wax very well?
No.
No. All right, so the waxy layer is very hydrophobic. Waxy layer for water retention. So that means that imagine that you have these leaves sitting out in the sun all day long. It's a good thing that, you know, that they're, because they need light to do photosynthesis, but then also you don't want too much water to escape. All right, so we have water retention. Then underneath it you have this thin layer called the epidermis, kind of like our skin. It protects and is a barrier between the inside and outside of the leaf. What's important here for photosynthesis is this mesophyll layer. So this mesophyll layer is, as we just said, it's the interior part of the leaf, because here's the epidermis at the bottom of the leaf. So the mesophyll layer is right in the center here. So this is what's used for photosynthesis. And notice here that if you look at these cells, you have, this is part of the mesophyll layer and this is part of the mesophyll layer. Notice that these cells are nice and stacked neatly together and they're nice and put together, and this is more haphazard. Sometimes they call this the spongy mesophyll layer because they're not packed very close together. So what happens is there's spaces, there's air spaces between them. And what that does is help to get gas exchange going on here. So now look at the bottom of the leaf, you have these stomata, the pores that open and close. When they're open, CO2 can enter, and because the spongy mesophyll layer has spaces in between the cells, then there's room for the CO2 to diffuse and get to all the cells to do photosynthesis. And the same thing when all these cells, after doing photosynthesis, they're going to release O2. The O2 can be released and go through the air spaces between these spongy mesophyll layers and get to the stomata to be released. And so it just allows for that gas to diffuse quite easily between all the cells doing photosynthesis and those stomata. Okay? And so that's the layer that's important for photosynthesis. Another thing that they have labeled here is the veins. So everybody knows, right, that leaves have veins. Do you guys know what the veins are for in the leaf? Do you know?
Or is it supplying water?
It is supplying water. So we talked how water goes in through the roots, and that there's this tunnel system called the xylem that goes all the way up to the top of the plant, and it goes through the branches and all the little twigs, and then brings water to the vein, through the vein to all the cells for photosynthesis. So when we say water is needed for photosynthesis, that's coming up from the roots and through the veins and getting to the mesophyll layers that way. So this carries, the vein carries water up from where? From the roots. You know what? The vein also does something else. Do roots do photosynthesis? They don't get any light, right? They're underneath the ground. They don't do photosynthesis. Do they need glucose for energy? Absolutely. And the plant needs those roots to stay alive, or else the whole plant's going to die because they're not going to get any water. So it's very important. So where's all the glucose made? In the leaves, and all these cells in the leaves. So guess what the vein does? Is not only brings the water up, but takes glucose down. All right. That's called the phloem. The xylem takes water up, and the phloem carries glucose down. Okay, so that's how things get in and out. So we talked about the water, the carbon dioxide. Now let's look at the sunlight here. So we enlarge a mesophyll cell. So here's one mesophyll cell. All these little circular things are the chloroplasts. So now we're enlarging a chloroplast here. And so when we look at the chloroplast, this is one thylakoid here. And so, so the thylakoid, remember, if we were to take this and look at it, if I draw it up here, has lots of pigments. So these are chlorophyll, which are pigments that absorb light. And so the light comes in and is being absorbed by all these pigments. So imagine this, all right? If you look at how many thylakoids are in one chloroplast. There's tons. They're all stacked up. Each one of these membranes around the thylakoid is important because the pigments. So tons of pigments in each thylakoid. Then look at in each cell. There's lots of different chloroplasts. And then each leaf has lots of different cells. So you can do tons of photosynthesis just in one leaf. And each tree has many different leaves and so on. So the plant is making lots of glucose through photosynthesis because of all these membranes that are helping to absorb this light with these pigments. All right. So moving on here. All right, so photosynthesis can be summarized by the following equation. So I'm going to have to explain a little bit with this equation. I'm going to write here, this is the real photosynthesis equation, and this is the reduced. So I'll give you a second to write the real one down here. And I'll explain. All right, so the reduced is what we just we've done here with the opposite of cellular respiration. So the reduces would be 6 CO2s plus 6 H2Os plus light energy. Gives you C6H12O6, which is glucose, and 6 waters, or 6 oxygens, and we'll leave out the 6 waters. So, in real life, okay, here the difference is this part here. What they did is, and I don't know why textbooks do this, because it seems like you can just leave it how it really happens. But in our textbook did this for cellular respiration. So a lot of places will reduce this and say, okay, if we took in 12 waters and you released 6 waters, we'll just say, we'll reduce it by 6 and say, okay, we'll say 6 waters are needed, the net waters, and no waters come out. That's what the reduced equation says. All right, and so that's what they did here. So when we learned about cellular respiration, the real equation for cellular respiration would be the opposite of this. So, the glucose plus oxygen, there is actually technically 6 waters that go in, and 12 waters that come out. And if you look real closely at the reactions in cellular respiration, you could see water coming in and water going out. What the AP test wants you to know is the reduced. But our book teaches cellular respiration like this with the reduced equation, and then throws in the real one for photosynthesis, which makes it confusing. So I just wanted you to know that they're really the same thing. All right, and so this is what you need to know. All right. Alrighty. Alright, so going on with the next slide here shows you, we'll look at the first thing that happens in photosynthesis is the splitting of water. Water is made of hydrogen and oxygen, so the water splits into those and incorporates the electrons of hydrogen eventually into sugar molecules. And so this picture here shows you where things go. And so mine is color coded to show where the C's and so when we take the C's and O's of carbon dioxide. So carbon dioxide, I'm going to put one color here. So the carbon and the oxygen of carbon dioxide is going to eventually become the carbon and oxygen of glucose. And so that's where when we make the glucose, that's the source of the carbon and oxygen atoms for glucose. The first step we said is splitting of water. So your water, H2O, so we look at the water, the oxygen of water ends up in the O2 that is released into the atmosphere. So when the water is split, oxygen is a waste product. The plant doesn't need the oxygen, it gets rid of it. And so that's your O2. So all the O2 that we're breathing in at any given second, all of the oxygen was once part of a water molecule. Somewhere along the line, a plant split a water molecule to create O2 that we breathe in. So then where does the hydrogen go? And so the key for the hydrogen is that the hydrogen goes along with the electrons. Remember, each hydrogen has one electron. It becomes part of the H's in your glucose molecule. And this is the main purpose of this whole process, is to get glucose. And so then notice that then the real equation that has 12 waters and 12 waters going in and 6 waters going out, so the leftover oxygen and leftover hydrogen go to making water molecules that are the 6 waste products. All right, the 6 H2Os as waste products there. So what we need to understand is how we make a glucose molecule. So glucose, the C's and the O's come from carbon dioxide, the H's come from water, and what we release, O2, goes into the atmosphere for us to breathe. All right, so that's the relationship there. So this process of doing that is a redox reaction, just like cellular respiration. So photosynthesis is a redox process in which water is oxidized and carbon dioxide is reduced. So why is water oxidized and carbon dioxide is reduced? If we look back again at this picture here, water, when the water splits, the electrons that are part of hydrogen meet up with carbon dioxide to form glucose. So therefore the water loses the electrons that were once part of hydrogen, and so the water is oxidized. The carbon dioxide gets those electrons and becomes glucose, so it gains electrons, so carbon dioxide is reduced. In photosynthesis, to do this, there are only 2 stages, so it's a lot shorter than cellular respiration. Cellular respiration, remember, there's glycolysis, intermediate step, Krebs cycle, oxidative phosphorylation. There's only 2 steps in photosynthesis. The light reactions, that's the photo part, they use light, and the Calvin cycle, it's the synthesis part, that's where you're going to make the sugar. And so we have these 2 stages that are kind of coupled together. So the first stage, the light reactions, that occurs in the thylakoids, in the chloroplasts, and they split water, and in that process releases O2, remember the O part of water releases oxygen, and produce ATP and form NADPH. Sounds an awful lot like NADH. And what was NADH?
Electron carrier.
Yeah, this is also an electron carrier. So it's going to carry electrons that were part of the hydrogen of water. So in the light reactions, remember what goes in? Water and carbon dioxide and light. So the light reactions, hence the name, uses light. to split the water. All right, so the water splits. The oxygen part of water is what leaves as oxygen in the atmosphere. So that leaves behind your hydrogens. Your hydrogens, along with its electrons, are going to go and be part of this electron carrier. And then the light energy also produces some ATP. So far, in the light reactions, no glucose is made. Hence the second step. The Calvin cycle, which occurs in the stroma, forms your sugar, your glucose, from CO2 using ATP and NADPH. And the ATP and the NADPH come from where? From the light reactions. So the light reactions make ATP and NADPH so that they can be used for the next step, the Calvin cycle, which is where your sugar is actually going to be formed. So the light reactions in itself doesn't make any glucose, but if the light reactions don't happen and they don't make ATP and NADPH, you can't do the next step, which actually makes the sugar, the Calvin cycle. And so this next bullet here, this word is very important. The Calvin cycle begins with what we call carbon fixation, incorporating CO2 into organic molecules. The organic molecule is something that contains carbon and used in a cell. So this is carbon fixation. So let's look at this picture here that kind of ties these two steps together. So here is your first step. So this is your chloroplast. This is your first step, your light reactions. And they wrote the word light reactions on the thylakoids to show that that's where they're actually made. The second step is the Calvin cycle. Okay. So then when we look in here, what happens at the light reactions is light is used. And so remember, light is absorbed, if this is the thylakoid here, absorbed by pigments, right, in the membrane. So this is pigment like chlorophyll. So it absorbs the light. And then that light is used to split the water. So the water molecule comes in. So I'm going to color code water, H2O. Water molecule comes in, and we'll look at the logistics later on, but the light splits the water molecule, and the oxygen part of your water molecule is going to go and be released as the oxygen into the air. So this is going to go back into the atmosphere, and the rest of us can take in oxygen and do cellular respiration and so on. So what are we left with then? We're left with the H's of the water. So remember that H's are one proton and one electron spinning around it. And we have two of those H's, one proton and one electron spinning around there. And so look at what else comes in. So notice here we have this arrow, NADP+. And notice that NADP+ is going to become NADPH. And this is very similar to how NAD+ became NADH. So we have here, so NADP+, if you take two hydrogens and when they come into contact with it, it's going to become NADPH plus an extra H+. And so let's look at why that is. And so you have two hydrogens left over from your water. So NADP+ has a positive charge because it lost an electron. So one of these, I'll get a different color here. So one of these electrons here from the hydrogen is going to come over here and neutralize that positive charge. So now you're left with an H+ ion. And then the second hydrogen that you have here actually just attaches to this molecule. So the second hydrogen actually becomes the H here. And then we have an H+ left over that's not used. So that's exactly like NAD+. And so NADP+ picks up two electrons and becomes NADPH. So it has one electron from one of the H's and the other electron from the other H. So this carries two electrons that were once part of water. I'm gonna put the H in for H2O. And in the process of that light energy, in the process of light reactions, some of that energy is used to make ATP. How do we make ATP? You add a phosphate onto ADP and make ATP. So that's why ADP and a phosphate are coming in as well, because in order to make ATP, that's what you need. And so these two things right here, ATP and NADPH, are the purpose of the light reactions. So far, what do we have going on here? The light came in, split the water, we lost some oxygen. We have the electrons that were part of hydrogen in these molecules of NADPH, and we have some ATP. So these two things are important because these two things are used in the Calvin cycle, which is taking carbon dioxide and making sugar. So therefore, the Calvin cycle can occur without the ATP energy from the light reactions, and without the hydrogen and electrons become part of the hydrogen of the sugar molecule. So these two things are needed for this to happen. And so let's look at this. So the Calvin cycle, it is a cycle kind of like the citric acid cycle, right? And so the citric acid cycle, remember, is a cycle that you start out with one molecule, let's call it molecule X. Here, a CO2 comes in and reacts with molecule X to form molecule Y. This process, taking CO2 and incorporating it into organic molecules in the cell, this is called carbon fixation. So we'd say that this carbon has been fixed. Carbon fixation, taking CO2 and putting it into organic molecules. Then Y gets converted to Z, and so on and so forth. So we have these series of reactions that go on in the Calvin cycle. But why it's called a cycle is after those series of reactions, we end up with going back to molecule X, and molecule X can now react with a new CO2, and so on and so forth. All right? So it's the same premise as the citric acid cycle in cellular respiration. So during this, so the CO2 goes in and goes through a series of reactions. During those series of reactions, in order to make them run, you need some energy for ATP. So there's your ATP. So ATP is used. When we use ATP, what do we break it down into? ADP and a phosphate. So that's why ATP is going in, ADP and a phosphate is going out. So some of those reactions need energy. The second thing going in here is the NADPH. The NADPH is carrying electrons. So what happens is the electrons from NADPH are going to meet up with carbon dioxide and eventually make your sugar molecule. So if I were to, let's do the carbon dioxide in red. So I'm going to put CO2 in red here. And eventually we're going to make our sugar. Notice here, they give you a generic formula for sugar. It says CH2O. What that means is for monosaccharides, there's twice as many hydrogens as there are carbons and oxygens. So notice here, glucose follows that. Glucose is C6H12O6. There's twice as many hydrogen as there are carbons and oxygens. So an example of the sugar would be glucose. If I were to color code my glucose molecule, according to how I color coded here, what color would my carbons be? My carbons would be red. The carbon of carbon dioxide becomes the carbon in your glucose. So I'm going to put C6. The H's would be what color? Blue. The H's were here, and I actually, when I did this, I could actually color code and make the H here. H was once part of that water molecule here, so I can color code that. And then this is going to meet up with these, so this is going to be blue. And then my oxygen should be what color? Red. All right. And that's what happens. And so when the NADPH drops off the hydrogen and electrons to make glucose, it becomes NADP plus again, and comes over here, picks up more electrons, and so on. And so these guys here constantly are going and shuttling back and forth to bring electrons in to be used for energy. And so then once the ATP is broken down, it's remade in light reactions and so on. So the light reactions are important for for the Calvin cycle because the products are needed for the Calvin cycle, even though the light reactions do not make glucose directly. That's an important first step. All right, so that's how these guys, these two steps kind of go together. So what we'll be looking at is taking the light reactions and looking more specifically at the light reactions, what actually happens when the water is split and what do these pigments do and so on and so forth, and looking more directly in that, and the same thing with Calvin cycle. So this seems like a good spot to stop.